Hey, this is Math 8, Unit 8, Lesson 6. It's called Finding Side Lengths of Triangles. Okay, so we're going to find some triangle side lengths today. So first of all, we have a little thing on which one doesn't belong. And so this is something you did in class today, is you take a look at the 4 different triangles here and have a conversation about which one doesn't belong. So if you're watching this in class for whatever reason, then you can press pause and have a little conversation about which one you think doesn't belong. Alright, some things you might see after you press pause and come back. So you might have noticed something like with this one here, this one here is the only one that is an isosceles triangle, right? Because it has 2 sides of the same. The rest have all 3 different side lengths. This one has 2 sides of the same. This one here has no 90-degree angle. It's only one. The rest all have 90s except that one. This one has no square roots, right? It's just whole numbers. And this one here has it has a right angle, which they all do, but it's the only one that doesn't have, if you notice here, kind of strange, no 5. It doesn't have any side length that has a 5 in it. So they each have a different reason why they maybe don't belong. So again, it's more about you having good conversations about what do you see and what do you notice there. All right, activity number 2 is it's called a table of triangles. And it wants you to complete the tables for these 3 triangles. All right, we have a triangle for D, E, and F. And what it's wanting you to do is look at the measurement for each one of these triangles here to figure out the lengths for the different triangles, okay? Alright, so when I look at triangle D, for example, I can tell you that the length for A is going to be 2. That's pretty straightforward there. But B and C, I'm going to have to do a little work to figure that one out, aren't I? Let's come back to it. When I look at E, I know that A is sitting here again at a length of 2. B is sitting here at a length of 1. And C is another diagonal. I'll have to come back and figure that one out. For F, I have A has a length of 2. But the other ones I just can't quite figure out. Now, we know how to figure it out in terms of drawing for ourselves, right, the kind of corresponding squares. So let's take a look at this first one, B. We draw lines from the vertices of the grid to make a square like so. And by making a square, we'd be able to find the area and then find a side length. So if I have this square here, pretend there's no triangle for now. If I have that square there, and I'm wanting to find out the side length of that square, then I draw for myself, in this case, I'm going to draw a square around that square to say that this blue square has an area of 4. Now I need to subtract from it these little triangle pieces here, and there are 4 of them. Now the triangle happens to be, and there's 4 of them, it's a 1 by 1, right? So that's equal to 1, but there are 2. So now I'm going to subtract the 2 full triangles, or 2 full squares, which is 4 triangles. So 4 minus 2 is 2. So the area of this square right here is 2. If that's the area, what's our side length? That makes our side length equal to root 2. So the side length for B is square root of 2. I can do the same thing for C, right? So here we're going to be going on the same column, going over 3, up 1. So we'll go over 3, 1, 2, 1, 2, 3, and up 1. So we're going to go there. And here we're going to go over 1, 2, 3, and over 1. And so we'll have a square that looks like this. So let's make it a pink color this time. So we'll go there. And we're going to go across here and here. Right, so here's the side length I'm looking for. And again, to find that side length, what I want to do is draw a square around it. Right, so I draw a square around it. And you don't even have to, at this point, you don't have to make a whole square. You can start to see how this is going to work. The area of this square is 1, 2, 3, 4. So our area of the square is equal to 4. But our triangle, long and skinny as it is, and there's 2 of them, is a 1 by 1, 2, 3. 1 by 3. So it means it has an area of 3, and there are 2. So we're going to subtract that. Oh, my area is not 4. So sorry. The area is 4 times 4 for this one right here, and 4 times 4 is 16. So 3 times 2 is 6. We're going to subtract 6. So what do I have? I actually have 10, is the area of this pink one right here. All right, you gonna come up here, friend? All right, my other kitten wants to play. All right, so we have an area of 10, and if that's the area of 10, that makes our side length equal to what? Square root of 10. So the side length for C is square root of 10 right there. Okay? All right, so for E, this one here, we had those two, so now we need to find this one. So we'll draw our triangle. We're going to stay same column and go up 2. Same little row, go down 2, and same row, go down 2. And again, to figure out what that's going to be, I can draw a square around this one. And I'm starting to notice that if I just do that much right there, I'm okay. Because even with that in place, I can tell that my big square is going to be equal to 3 by 3. So it has an area of 3. And my triangle then is a 1 by 2. And making that square becomes a value of 2. And there's 2 of them. So it's going to be minus 4, so I'm left with 5. So the area of my triangle or square here is 5, meaning the side length is square root of 5. Alright, square root of 5 for my side length equals square root of 5. So now when I get to this next one, same idea. We're going to be in the same column and moving over 2, so we have that going there. This one's going to kind of fall off of the edge, so to speak, right? We don't have space for it to fit. So it would go there, it would go there. We don't have space, that's okay. That's our side length for that one. This one goes here, it goes here. Oh, same ones right here. And it goes here. Okay. This triangle here, what I notice about it so far, just by looking at kind of the shape that it's in, is it sure does look like they're pretty close to each other, but we know it's not quite equilateral. But we know that these two sides are going to be the same. So whatever I find for C, it's going to be the same for B, just because of the nature of how this one is shaped. They're the same starting point. So let's find what that triangle, what that side length is going to be. To do that, I'll draw a square around this one. We have a 3 by 3, so the green square is an area of 9. The triangle shapes are a 1 by 2, and again that makes it have an area. Oh, hello. What's going on there, Stevie G? So sorry guys, my little kitten here has come to visit and wants some attention. Alright, so we have an area here of 2, and we're going to multiply that by 2, which becomes 4, but now we'll subtract. So 9 minus 4 is 5. So the area of this shape is 5, which makes our side length what? Remember how we do this? Square root of 5. And that's our side length for that one right there. So it's B and C are the same, so I can just write down here square root of 5, square root of 5. So a lot of work there to get those numbers in place, okay? But we're trying to build some understanding here of how this all works together. Notice that in our triangles, when we look at them, they are a little different, right? This first one is an obtuse triangle. The second one is a right triangle, and this one is an isosceles, but it's also an acute triangle. We don't have any obtuse angles there, okay? So now when I take the values, that I have up here, it wants me to square them, okay? So for D, if I take 2 and square it, what would 2 squared be? Let's say 4. What is the square root of 2 times the square root of 2? Square root of 2 times square root of 2 simply equals 2. And just like that, the square root of 10 times square root of 10 equals simply 10. When I do this one, 2 squared is 4. 1 squared is still 1. And the square root of 5 times square root of 5 will be 5. And down here, 4 squared is still 4. Square root of 5 times square root of 5 is 5, and 5. So that's how that works out. A lot of work, I know, goes into finding these side length values, but it's for a good purpose, okay? So, what do you notice about the values of the table for triangle E, but not for D and F? So what do you notice about these values for E that you don't notice for D and F? Okay, give it a little moment there, take a look at it. What do you notice? What's happening there? What's taking place? Well, hopefully, press pause, your teacher gives you a chance to check that out. Hopefully what you're noticing here with E is that when it comes to E, the side links here, or the squared values, the 4 plus 1 equals 5, right? That's the only one that works. 4 plus 1 equals 5. That doesn't work in any way. There's no connection there. It doesn't go together. So what we're really seeing is recognizing that, man, it looks like the a squared value plus the b squared value equals the c squared value. Now we also notice that's only true for triangle E, and the one thing that triangle E had that the rest did not have was what? It had a 90-degree angle. So when you're a 90-degree angle, or a 90-degree triangle, we're making sense of what we have as an a squared plus a b squared equals c squared. Interesting. Well, let's do some more and see if we can continue that and find a similar pattern here. Okay? So we're going to turn the page, looking at number 3. Number 3 says to complete the pattern, tables for these 3 more triangles. So again, a little bit lengthy process here, but let's work through this, all right? The a value is 2, a value is 2, a value is 2, a squared is going to be 4, 4, 4. That was the best part. This b value for q is 1, 2, 3, so 3, and 3 squared is going to be 9, and that's as far as we can get, right? Now we have to find out the side lengths of these other triangles, okay? Which we can certainly do. So let's take a look at this first one here. We're going to draw the square out to there, and this one goes out there, we can't quite see it, and out there we can't quite see it. So for the b value, if we were to finish this square up, where would it be? Well, it would go to here. I can't do the whole thing, so I'm just going to kind of etch out what I can. Something like this, right? So in terms of how long it would be, we can see that we're going a length of 2 and a height of 1. Look at this triangle here. It's a 1, 2, and a 1. So we're going to have a 3 by 3 blue square, which means it's sitting there at 9. Right, so it's sitting there at 9 for that one there, and then we have to subtract the triangle pieces. The triangle is a 2 by 1, or put it together you get a 2. There's 2 of them, which makes it 4. So 9 minus 4 is 5. So the area of this triangle, square inside, sorry, is 5, which makes our side length for B equal to square root of, something's a little off my notes here. Square root of 5? Can't quite tell what I said there. Should be square root of 5. I got that right. 9. Doing it right here. My notes seem a little off. Sorry. Let's re-verify. So we have the square. We have the square. We go out to there. 3 times 3 is 9. And then we have a 1, 2 by 1, which is 2. 9 minus 4 is 5. And then that becomes a square root of 5. I think we're okay. I still think we're okay with square root of 5. I'm going to leave it for now, okay? Alright, and then I look at the next triangle here. We're going to go, looks like we're going down 1, 2, and over 1, 2, 3. So we're going to go up 1, 2, and over 1, 2, 3. Let's go here. 1, 2, 3, up 2. Oops, that didn't quite work out too well, did it? That's not so nice. So we're going to go here. Over 2 spaces. So 1, 2, 3 up to there. So that's where we're going to get there. And then moving up 3, 1, 2, 3, and over 2 spaces, so about here. And about here is what that triangle looks like there. That's a little bit out there, I know. So there's our triangle for that, our square for that one. So to make a bigger square around it, would go up to here, out to there, and out to here. Okay, so in terms of how far out that is, we are going to be going out 1, 2, 3, 4, 5. So a 5 by 5 square. A 5 by 5 square is 25. Okay, so that's 25. Then I have this little triangle thing here. And the triangle shape seems to be 1, 2 across, and then 1, 2, 3 down. So that's going to be a 2 combined grid of 6 times 2 is 12. So let's subtract 12 for our area, and we end up with 13 is our area, which means the side length will be square root of 13 for C. So square root of 13 goes there. So when I come down here and square this, what's the square root of 5 squared is 5, and the square root of 13 squared is 13. Okay? Now let's take a look at this C one here. We're going to be going, looks like here, 2 across and going down 3. So 2 across and going 2 across and going 3. So about here. Yep. 3. Yep. And then we're going to go 3, 1, 2, 3, and 2 up. Right there. And there is where that one's at. And so this little triangle, it's going to come, and we can do it however we want here. We can come down this way if it helps, and go across this way, and that way. We can do a bottom one, right? It goes up, that's our big square. So for this big square, we're sending that 1, 2, 3, 4, 5 across again, so it's still 25. So 25, and then we have the triangles we got to chop off. In this case, the triangles we're chopping off is this one here, 1, 2, 3 by 2, which is the same as the last one, isn't it? 3 by 2, which is 6 for our triangles. So that's going to be 6 times 2 is 12. So we're going to subtract, and we end up with 13 again. So this triangle is also going to be a 13er, which means that our side length equals square root of 13. If we did that right, and that side length here would be 13 right there. Okay, and then let's do this one here, C. We're going to go over 3. We're going to go over 1, 2, 3, so about here, and then down. So that's our square for this one. And as we draw the shape in, we can see we already have a triangle there. We can go up. We wanted to complete that whole square to find out the big area. The big area is going to be 1, 2, 3, 4. Right, so we're 4 by 4. So the big area here happens to be, in this case, looks like 16. The triangle pieces are going to be a 1, 2, 3, and a 1. So 3 by 1. So that makes it into a square that's 3. And there's 2 of them. Times 2 is 6. So it is 16 minus 6, which becomes an area of 10 for our square, which makes our side length equal to square root of 10. So, and then it's the same, these are the same lengths. This is square root of 10, square root of 10 for R, yeah. So, the square root of 10 squared is 10, and then 10 again. So, once again, what do you notice here about the values in this table? Take a look at those values. What do you see? We see we have 4, 5, and 13. No real connection there. 4, 9, and 13. Well, again, 4 plus 9 does equal 13. 4, 10, and 10, no pattern there. Again, this is the only one Q that has a 90-degree angle. It's a triangle. And so what we can see is that when we take the values of A, B, and C, and we square them all, that A squared plus B squared is going to equal C squared in terms of our values and what we see happening. And this is true for our right triangles. They have to have that 90-degree angle in it for that to make sense and that to work. Okay, so the one thing that triangles E and triangle Q have in common, which is what we just said, is they are both right triangles, aren't they? Okay, so 6.3, meet the Pythagorean theorem. Find the missing side lengths. Be prepared to explain your reasoning. For which triangles does A squared plus B squared equals C squared? All right, let's see what we have here. So this one here says that the value is of this length is A is root 8. That means that B is also going to be root 8, and the reason for that is because we have an isosceles triangle. This is the same distance, so it makes sense of the same. This length, though, is going to be simply 1, 2, 3, 4, because it happens to be 4, all right, 4 across. So, does root 8 squared plus, right, this is our A squared, plus our B squared, plus root 8 squared, equal C squared? Well, square root of 8 squared is simply 8. Square root of 8 squared is 8. And then 4 squared is 16. 8 plus 8 is also 16. So does 16 equal 16? We would say yes it does, right? So are we okay with that one? Does that make sense? Right? So our missing side lengths are figured out there, and then we're able to show how those work together. So that worked out pretty well. Let's try another one. And lots to practice here too, okay? So we have side lengths given to us, root 10, root 40, and this one we don't have. So I'm going to have to figure it out by making a measurement for the side length. I'm going down 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. So we're going to go down to here, connect that line right there. And then we're going to connect this one down to 1, 2, 3, 4, 5, 6, 7. And go down over 1, I should say. And we'll get that lined up right there. So here's my square. It's my inside square in order to find a side length. But to find a side length, what do I have to have? I need to know the area of the square that goes around that one, and then subtract the triangles. So the big square is 1, 2, 3, 4, 5, 6, 7, 8. That's an 8 by 8 square, which is 64. Then I need to get rid of these triangle pieces. The triangle pieces are sitting here at 1 and 1, 2, 3, 4, 5, 6, 7 right there. So I have a triangle that is 7 by 1. And if I match the other side up, I have two triangles, 1, 2, that make a square, a rectangle, and that's 7. And because if there's another set over there, I can multiply that by 2 and make 14. Subtract 64 minus 14, and I end up with 50. So that my side length is going to be equal to square root of 50. Okay, so this side length right here is square root of 50, which makes C, equal to square root of 50. So let's see what happens here. Can I get A squared plus B squared equals C squared? Let's just see. If I did this here, A squared plus B squared equals C squared. So we'd have root 10 squared plus root 40 squared equals root 50 squared. Is that true? Well, the square root of a square root is going to be simply the number 10. Square root of a square root is going to be the number, which is 40. And then the square root of a square root is going to be 50. 10 plus 40 is 50, so this is going to be true for our little theorem right there. It's working pretty well. Okay, well, let's look at the next one here. Here we have some values. We have root 17, root 5, and then 1, 2, 3, 4. So A is equal to 4. That's what we have so far. So now we go back to our formula. A squared plus B squared equals C squared. Does this work? 4 squared, and then B is root 17 squared, and C is 5 squared. 4 squared is 16. Root 17 squared is 17, and then 5 squared is 25. This adds up to 33. 33 does not equal 25, so this is a false statement here. But of course it's going to be a false statement. What do you notice? What is this triangle lacking? What does it not have? We would say there's no right angle, right? There's no right angle in that one, so it's not going to work out. You have to have a right angle in order to use this little theorem right there. Okay, so that's kind of your main idea today. So let's take a look at your summary here and wrap it up before we get on to our homework stuff. In summary, a right triangle is a triangle with a right angle. In a right angle, the side opposite the right triangle is called the hypotenuse. It's a new word there for you, hypotenuse. The other sides are called its legs. Here are some right triangles with the hypotenuse and legs labeled. So what helps me a little bit is, remember, if you kind of get lost, it's the one that, take an arrow, is across from the right angle is your hypotenuse, right? Here's your 90 degree, so across from it is your hypotenuse, across from its hypotenuse, and across the hypotenuse. The other ones are your legs, okay? Your legs are always your A and your B, and your hypotenuse is always your C when it comes to the formula. So we use the A and B to represent lengths of the shorter sides of the triangle and C to be the longer side. And so if that's how that works, you end up with something that looks like this: A and B and C. Okay? All right. So when we take a look at some triangles and some samples here, we see that when we look at these samples, what happens is you can use the squares, and what you find is that when you add up those squares, they add up the sum of to the sum of the larger square, right? So this line length, side length, in making a square is an area of 9. This one's 16, and 16 plus 9 do add up to be 25. And as long as you have a right angle there, this is going to work in all situations. So notice that for these examples of right triangles, the square of the hypotenuse, and there's actual or literal square there, is equal to the sum of the squares of the legs. Notice it's both squares of the legs. So that's always the case. This is the property of all right angle triangles, not just these examples, and it's often known as the Pythagorean theorem. Okay? And that's really what today's lesson is about, the Pythagorean theorem, which is a special thing of right triangles. It says that a squared plus b squared, or the two short legs squared, equals c squared. All right, so pause there, do some homework, and let's come back and check it together. Number 1, here's a diagram of an acute triangle in 3 squares. Priya says the area of the large unmarked square is 26. So she says this is 26 because 9 plus 17 is 26. Do you agree? And explain your reasoning. So what Priya is saying is that she's saying, well, we know that a squared plus b squared equals c squared. So if these are the two smaller ones, and you have the square there, which is 9, and the square here is 17. Notice I don't have to do any more. The square means that area sum. 9 plus 17 is 26. While that might be true, there's one key thing that Priya forgot. This is only true for what? Only true for right triangles. So, do we agree with her? No, we don't agree, because why? This is not a right triangle, and so it cannot be right. Number 2, M, P, and Z represent the lengths of the 3 sides of this triangle. All right, notice that M is our hypotenuse, right? So this is functioning like the A, the B, and the C. Select all the equations that represent the relationship between M, P, and Z. So what we know is that these two things summed up together after being squared have to equal the M value. M's our big one. So for A, M is not the equal, it's not the sum, right? It should be on the side. So this is going to be no, that's a no. Here, M squared is there, that's good. So we're doing P squared plus Z squared, that looks great. Looks great. Here, M squared is what we're summing up to, which is perfect, and it's Z squared plus P squared. Order's different, but it doesn't matter as long as the M squared is by itself, and those are being the sum of the two legs, we're okay. Over here, they're including the M with the P. They'll never add up to match the Z, so that's a no. Here, we have Z squared plus P squared equals M squared. Again, the M squared is by itself, and the sum of those, that looks great. And F, M squared is by itself, and the sum of those, that is great as well. So we have 4 good answers right there. Moving to number 3. Number 3 says, the lengths of 3 sides are given for several right triangles. For each, write an equation that expresses the relationship between the lengths of the 3 sides. So these are all valid lengths of right triangles. So let's write an expression that shows it's true. Okay, so let's do this. For this first one, we'd probably go with 6 squared plus 8 squared equals 10 squared. And if you work that out, what you come up with is what? 36 plus 64 equals 100. Over here, looking at this one, we're going to say the square root of 3 squared plus the square root of 5 squared equals the square root of 8 squared. So again, those are going to get eliminated, and it switches over to become 3 plus 5 equals 8. Down here, this one's a little funky, but it does work. We have 5 squared plus root 5 squared equals root 30 squared. Again, 5 squared becomes what? It becomes 25. Root 5 squared becomes simply 5. And then square root of 30 squared becomes simply 30. 25 plus 5 equals 30, so that's good. Alright, this next one, we would do 1 squared plus, here's a 6, let's do 6 squared equals the square root of 37 squared. Why? Because that becomes 1 plus 36, which equals square root of 37 squared is 37, and 1 plus 36 equals 37. Alright, for E, we have 3, root 2, and root 7. Alright, so be careful about this because the square root of 9 is actually 3, right? So this number here is less than 3, so our biggest number we're working with is 3. So we're going to do root 2 squared plus root 7 squared equals 3 squared. Root 2 squared is going to be what? 2. Root 7 squared is 7. And then 3 squared is 9. So 2 plus 7 is 9. So make sure you get your order right when you're doing those things, just being careful that you got the right numbers you need. Alright, order the following expressions from least to greatest. Okay, 25, going to divide it by 10, move the decimal over 1, so that becomes 2.5. Dividing by 1,000 means move the decimal over here, like it says 3 zeros here, we're going to move it over by 3 spaces, so 1, 2, 3, that becomes 250. To move this over 3 spaces, we're going to go 1, 2, 3, so that becomes 0.0025. And if we're going to divide by 1, we're actually going to go the other way and move it this direction, and that becomes 0.25. So least number, smallest number is here. That's our smallest, followed by this one, followed by this one, followed by this one. Number 5, kind of funny little problem here. Which is the best explanation for why the negative root 10 is irrational? And they got a lot of funny things in here, but the best answer is actually going to be here. It's irrational because it's not rational. That's what irrational means. It means basically not rational. That's the best explanation. Being less than 0 doesn't matter, whole number doesn't matter, calculus doesn't matter. The reason it's irrational is because it's not rational. That's all it means to be an irrational number. It means you're not rational. Okay, a teacher tells her students that she is just over 1.5 billion seconds old. Way to go. So she's 1.5 billion. So that's 1.5, scientific notation, times 10. And how many zeros are in a billion? 9. Right? She's 1.5 billion seconds old. 1.5 times 10 to the 9th. I'm going to use that information over here. 1.5 times 10 to the 9th. What is a more reasonable unit of measurement for the situation? Rather than seconds, she probably should talk about how old she is in years. It makes a little more sense. Even months would be better than seconds. So how old is she when you use your more reasonable unit of measurement? If I use years instead. Okay, well, let's think about it this way. There are 60 seconds in 1 minute, right? And there are 60 minutes in 1 hour. There are 24 hours in 1 day, right? And there are 365 days in 1 year. All right, that's like my conversion that I have to play with here, right? So this is going to convert how many seconds are in an actual year. This is what I'm looking at, right? How many seconds are in a year? I can figure it out this way. So 60 times 24 times 365 is actually equal to 31,536,000. All right, that's a nice big number. So we know that she is 1.5 times 10 to the 9th seconds old. And we're going to go here and then put this in scientific notation as well. This becomes 3.1536 times 10 to the, we're moving it 1, 2, 3, 4, 5, 6, 7, 8, 7, sorry, to the 7th power. Okay, so what is 1.5 divided by 3 point that times this, and it's being times 10, you end up with about 47.6, about how old the teacher is. Alright, that is it for today. Have a great one, and we will see you next time.